All right, hi everyone. My name is Daniel, and today I'll be presenting on ViralWasm, a client-side user-friendly web application suite for viral genomics. And this paper was authored by me, Dr. Robert Bukalel, and UCSD Associate Professor Nima Moshe. And this is pretty different from the neurobiology talk and computational talk that was pretty given just now. But yeah, I'd like to start off with the problem statement that we're looking at with computational tools in epidemiology. So the goal for usually public health officials and epidemiologists is to get fast and accurate diagnosis of patient viral sequences. And that means taking raw sequence data and performing viral diagnosis and mutation evolution. But when you're trying to do this as a public health official or epidemiologist, you run into some roadblocks. And so the first is a learning curve. So usually you have to have a computer science background and some technical know-how to kind of operate these tools. And that includes installing software, using the terminal, even using Linux. And so this is just an example of some poor experience someone might have trying to figure everything out while getting these tools set up. And so this is further exacerbated when you have to use 3 to 4 molecular sequencing programs per job. And picking the tool that you want to use is already difficult, as well as these tools sometimes require dozens of dependencies and prerequisites. And then for regular users, maybe say someone working in a lab on a workstation without administrator access, these installations can be nearly impossible. And so now, instead of actually using tools, users now have to worry more about successfully installing the tool. Continuing with some problems that epidemiologists might run into, there's data and server concerns. So if you decide to not use your own local machine to run these molecular sequencing jobs, now you're sending it to potentially a third-party server. And with this data being sent, then there's the obvious concern of what's happening to your data. And if you have your own in-house servers, then you have the question of if you have your servers always on, then you're incurring a high cost. And if they're cold boot, then you have long boot times to the point where using the server or booting the server to run the job might be taking longer than running the job itself. And finally, if you have remote area limitations, maybe you're in somewhere like sub-Saharan Africa where you don't have internet access, then you're forced to resort to using your own machine, and you can use something like a third-party server. And so we present our solution, ViralWasm. So ViralWasm is a web-based end-to-end molecular epidemiology pipeline, as well as some standalone tools. And this all the code compiles directly from source code. So there's no need to rewrite any of the existing tools in web-based languages like JavaScript. So it's complete client-side functionality. These tools and these pipelines are now completely running in your own browser. So there's no server that runs on your Chrome browser, your Safari browser, your Firefox browser. These tools are ported to the web client side. And so instead of having something like C, C++, or Python compiling down to machine code, we're now compiling down to WebAssembly that runs in the browser using the JavaScript engine. And so once these tools are deployed on our end and you access them either on the web, they're instantly ready to go out of the box. The user experience has a clean and intuitive interface for uploading your data. I guess uploading might be a poor choice of name because you think it might be going to a server, but still staying in your browser, but now just being loaded in memory. And the parameters can be adjusted via the user interface. These are also offline capable. So the website and the tool can be downloaded for offline use just through a few clicks. And so this solves the issue of remote area limitations. So for our technical approach, we have 2 primary pipelines. The first pipeline is for multi-sequence alignment, molecular clustering, tree inference, and routing and dating. And it uses viral MSA, that's for sequence alignment. Minimap2 is also for sequence alignment. And then FastTree2 is for tree inference. And then LSD2 is for routing and dating. ViralWasm Consensus does consensus genome generation. And you can do optionally if you want to do sequence trimming before that, but that uses Minimap2, FastP, and viral consensus. And then for the web technologies, we use Mscripted and ViralWasm, which both help compile the code down to WebAssembly. ViralWasm is actually built by Dr. Robert Abuka, who's a co-author on this paper. And then PyDot runs Python code in the browser, and React is the front-end framework, and then Bootstrap is just to make it look pretty. So after we built the apps, we wanted to compare how it performs against the conventional command line tools. So we used a Playwright testing framework for accuracy and performance benchmarking of the ViralWasm web app. So Playwright just simulates a page browser and then automates the user input and the tool running to see how it compares against the command line. And so these benchmarks ran automatically on every push that we committed to the code base via GitHub Actions using the command or using their workflows. And so these ran on GitHub's machines on their servers, and it ran on a Ubuntu 22 machine with 2 processor cores and 7 gigabytes of RAM. And then, so comparing the web versus the command line benchmarks, the web scales reasonably in terms of memory and runtime. It's a bit slower, and I'll have some graphs, but you can take a look on the left. So that's, I don't know if it's cut off, but on the left, that's the memory usage. So there's about maybe a 500 megabyte gap between command line and the web interface, but that's pretty reasonable for workstations nowadays, where you can have 4 to usually 16 gigabytes of RAM. And then for the runtime, even when you're up to 400 genomes and you're running, the large bulk of the runtime in the memory is when you're trying to do tree inference and routing and dating, or tree inference, but even when you're hitting the higher numbers, you're only slowing down by like 50 seconds or so out of a comparison between a couple minute run. If we look at ViralWasm consensus, for the memory, it starts at around 400 megabytes, and then it jumps all the way to 900, which is still pretty reasonable for a workstation. And with 400,000 reads, that's pretty large for even an individual health department. So that should be manageable. And then for the runtime, it's maybe a difference between 85 seconds and a minute. So not too bad for the slowdown. And yes, so for results, we see that there's a relative slowdown compared to the command line by maybe 2 to 3 times at worst. But it's good to note that these tested data sets are large for even individual public health departments. And then these job times are still reasonable for even laptops and tablets. And they're often less than a minute, and at worst, around 5 minutes. And we think it's a worthwhile trade-off to have the general use and accessibility of these web apps as compared to the command line interfaces. So moving forward, we definitely like to look into scaling to larger data sets, as well as reducing the web app / web assembly overhead. And that might be even utilizing the web GPU to achieve those speedups, as well as reduce the memory overhead. And another thing in maybe the grander scheme of things is having automatic tool creation to the point where instead of having to code these web apps manually, we can automatically port bioinformatics tools to the web using WebAssembly so that they run the browser. And it'd be more of a general use case. Yeah, we can go ahead and give a live demo. Open the link. Okay, so here you have the 2 core pipelines, the consensus and epi, and you also have some standalone tools. But we can open this up. And so this is ViralWasm epi. It takes a bit to just load everything into memory, the tools from online, but you have the left, you have the input, and then on the right, you have the output or the console. And here's where you would like enter or submit upload your files and change the parameters. We can just look at sample data. Okay, and then we can maybe perform molecular clustering. You would change whatever you need to. There's already some default parameters, and you just hit run. And then on the right, this is usually the command line output you'd see if you ran it in the command line. It can be helpful for debugging and whatnot. And then you can just download whatever file. So we can like download the alignment. And so yeah, and this is the alignment that's done on the sample data that we have on the site. And then it gives the runtime. If you want to run it offline, maybe if I have time to do this, you would just download a zip file and then take a second to download. You can maybe just show the one. And then all you'd really have to do is extract it. And so this is hopefully a lot easier than having to install all these tools on your own. Then there's a Python file that you run. So hopefully they have Python installed. That's just the one prerequisite. And then now you have it running on localhost, so your own computer. So even if you didn't have internet access, everything would still run fine. And it's the same exact interface. But yeah, that's basically all for the presentation. Thank you for listening. Please let me know if you have any